So welcome to the webinar 8 of the webinar series. We, Professor Anirban Datta from University of Buffalo and myself, Professor Uttama Lahiri from Indian Institute of Technology, Gandhinagar, are jointly organizing a webinar series on translation and research in neuroengineering and neurorehabilitation. In this, we have speakers from different parts of the world and delivering talks on emerging applications of neuroengineering while covering topics in engineering perspectives to neuromodulation, cost-effective technologies used in neurorehabilitation, and the clinician's perspective to neuroengineering. Namely, our first speaker was Dr. Subhranu Dey from Resner Polytechnic Institute, and he gave a talk on the non-invasive brain imaging for bimanual surgical skill assessment. Following that, we had the webinar 2 series, again an exciting speaker from industry, iTech Digital Systems, Keith Jackson. He spoke on the eye movement data, how it can be used to assess brain health. The third speaker of the webinar series was Professor Sue Ann Sisto from University of Buffalo, and she was speaking on spinal cord neuromodulation. The fourth webinar speaker was Professor Michael K. Stakubiak, and he was speaking on optogenomic approaches to neurorehabilitation disorders. The fifth speaker was Professor Suresh Devashayan from the Christian Medical College in the South Vellore in India, and he was speaking on functional electrical stimulation for exercise and ambulation in paraplegics. The sixth webinar speaker was Professor M. Manivanan from IIT Madras, and he was speaking on applications of virtual reality towards rehabilitation. Our seventh speaker was Professor Chandramouli Krishnan, and he was speaking on robotic rehabilitation and laying its future pathways and what's the current state in order to maximize the delivery, the recovery. Our eighth webinar speaker today is Mr. Thomas Johannsen, and he would be speaking on the functional near-infrared spectroscopy, which is fNIRS in short, for neurorehabilitation and neuroengineering. Before we start, let me give a very brief introduction about our speaker today. Thomas Johannsen would be speaking on this topic of fNIRS. He has worked in neuroimaging for the past decade, starting first with electroencephalogram, that is EEG, and transcranial magnetic stimulation, TMS, before moving into functional near-infrared spectroscopy, which is in short fNIRS. In his role as vice president with NIRx Medical Technologies, he plays an integral part in ensuring the company's customers, researchers, and collaborative partners, they are productive and successful with their fNIRS studies. NIRx, which was founded in 2000, has become a leading fNIRS manufacturer with over 850 active labs in 50 countries and a reputation for releasing cutting-edge technology that pushes the boundaries of signal quality and usability. Additionally, I will also introduce Dr. Mahipal Chaudhary, and he is also very much an expert in the area of the fNIRS, and he will be also walking us through some of his presentations in today's webinar series. So nice to have Mr. Thomas, our speaker, and Dr. Chaudhary. Over to you. The floor is yours.
Fantastic. Thank you so much, Professor Lahiri, as well as Professor Datta, all that have been involved in the organization of this series. We're truly honored to be invited. We would like to also extend our thanks to Indian Institute of Technology, as well as the University at Buffalo. Now, to get into making sure my screen is shared up and that everyone can see it, just a couple clicks here, and we should be ready to go. Okay, I'm just going to confirm that you can see my presentation now. Fantastic.
Okay.
Now, this presentation today is on fNIRS in neurorehabilitation and neuroengineering. Let me move my video to the side there a little bit. We're going to start off actually with why fNIRS for neurorehab and neuroengineering. We realize that it's in the evening here. Maybe some of you need to get some food, and we wanted to just jump right into it. Why even care about this? So we'll give some case examples and actually get right into a live demonstration. My colleague, Dr. Mahipal Chaudhary, will be able to show that. We will then get into the basics of neuroimaging with fNIRS. So you'll get to understand more in that section, as well as the challenges to consider. This is really critical, as I'm sure you all know, when using any sort of novel technology for your lab and your research, to understand really the challenges that you might encounter and very often will encounter, and how to address those. Now, there are strengths, of course, in fNIRS, and we want to get into that a little bit later, as well as some additional cases that we didn't quite fit at the top of the presentation. We'll have some time for questions as well, I understand. And I did just want to do a quick time check again, or rather, if anyone has a chance to just message, let me know to make sure that we have how much time I do have. But yeah, we'll get into about us. So, as already mentioned very nicely about NIRx, we are a manufacturer and developer of fNIRS complete solutions. That was founded in 2000. So we provide hardware, we provide software, we provide very in-depth lifetime technical support for our end users to make sure that they can be successful, and you all can be successful with our technology should you use NIRx fNIRS systems. We are located all over the world with headquarters in Berlin, Germany, where Mahipal is, as well as Minneapolis, Minnesota, where I am in North America. And here's just our faces again. You already saw myself and Mahipal, and you'll see us more, but we'll keep on moving right into the next section. Why fNIRS for neurorehab and neuroengineering. So it is a very flexible imaging tool to use for various environments and stimuli. It does set up in minutes. It can be portable and wearable, not necessarily, but we see portable wearable examples here, and that's what we'll be showing today. It's very good for real world and naturalistic environments and tasks. It can be used in multi-subject interaction studies as well. See again an example of that. It's very robust to motion artifact as far as neuroimaging techniques go. In fact, we argue that it's the most robust neuroimaging technique versus EEG, fMRI, PET, and we'll get into why that is later on. It is a safe technique, it is silent, and it is also very comfortable. There's a bit of subjectivity to these points, but generally speaking, it's not too difficult to achieve these so long as you actually evaluate your equipment a little bit before you purchase it. You can image a very great range of participants given these factors, and it sets up incredibly quickly, which has already been mentioned a little bit, but I wanted to emphasize that as a point here as well. So if people are normally not too capable of sitting for really long periods of time because of setup, that is a nice factor with fNIRS. It can be combined with nearly any other modality. It is optical, so it uses light to gather the data, and does not cause noise in other imaging techniques, nor does it receive noise from other imaging techniques. You can measure more components of the hemodynamic response compared to old fMRI. We're specifically measuring oxy, deoxy, and total hemoglobin. And fMRI, by contrast, focuses primarily on deoxygenated hemoglobin. Now, it is also lower cost than fMRI, though it's not a one-to-one comparison, of course, because you're getting deep brain structures as well as function with fMRI. We do not measure the structural image with fNIRS. It's just a functional imaging technique like EEG, but it is comparable to a high-end EEG system in terms of price. So you could own your own system or own it jointly with another group and really be able to use that very, very productively compared to having to book time with fMRI and having the studies take a little bit potentially longer. as a monitoring tool and getting a little bit into general applications for neurorehab and neuroengineering, it is a very effective imaging technique. That is, you can investigate mechanisms of functional recovery after brain injury, such as stroke or traumatic brain injury. Investigating neural rehab basis of motor learning has also been done, and gait and balancing control is also very often done with fNIRS in these applications. We see that BCI, brain-computer interface, is a major area of fNIRS's actually maturity, we could even say at this point, compared to other areas, where it has been used very successfully, very often in combination with EEG and other techniques for real-time analysis purposes. Relatedly, another real-time application would be neurofeedback. Now, I'm going to keep moving on just to make sure that we're efficient. I wanted to get into case studies next. So we just picked out a few samples of some nice case studies from recent years, but there are many more examples, and please feel free to get in touch if you don't see something that quite piques your exact interest, as chances are there may already have been something done in that realm that we can refer you to. This particular publication was BCI with neurorobotic rehabilitation. It is basically showing a novel functional near-infrared spectroscopy based brain-computer interface, again BCI framework, for control of prosthetic legs and rehabilitation of patients suffering from locomotive disorders. So you see a little diagram there. It's an excellent publication. In 2019, we have Muller et al. In this case, it was a limb prosthesis and gait analysis that was done using fNIRS. We can see the montage of the prefrontal and motor areas. And moving on, we also wanted to show this example, which was looking at TDCS, that is transcranial direct current stimulation for treatment of depression post-stroke. Now, you may know that with any sort of electrical stimulation, that can be a very big issue for EEG. In fact, it is a big issue for EEG simultaneously when you're looking at the stimulation. Not that EEG can't still be done, it's just the signal in the EEG does have challenges in actually measuring the activation. And so enter fNIRS, as mentioned already before, that it is an optical imaging technique that does not receive interference from other techniques because of it being a light-based measurement. So we see in this example that they measure the prefrontal cortex and we're able to see essentially enhanced aerobic metabolism in these post-stroke subjects. Now, there are many other studies, as already mentioned, and we'll now get into the live demo. So with that, I'm going to welcome back my colleague, Dr. Mahipal Chaudhary, who is in Berlin, and he will be able to share his screen and share his demonstration there. So Mahipal, if you could share your video, and I'll stop sharing my screen now.
Thanks a lot. We have a few minutes, and I'll try to give you a brief impression of how the equipment looks like, how the setup looks like. We can't go into too much details given the time constraints, but I think you'll have a fair idea of what I'm talking about, or what fNIRS looks like at the end of this talk. The device is, I'll be using our portable device, connects via USB as well as Wi-Fi. I'm using the Wi-Fi to talk to you, so I'll connect with the USB. In terms of the cap, this is how the cap looks like. The cap is basically, if you have any EEG experience, then it's mostly an EEG kind of cap. It has EEG landmarks labeled as well, depends on the manufacturer as well. And the cap basically consists of sources of light and then detectors that can detect the light, right? And the arrangement will mostly be a matrix like this. The sources and detectors will be separated by a certain distance. And that certain distance is determined by what kind of participants you are studying, basically. A standard is about 3 centimeters. Thomas will talk about that a bit later. To give you an idea of how the setup will work, one thing you may already appreciate is I'm not able to see all the participants, but given that I'm from India, majority of the participants are also from India, I have good, thick, dark hair. And I can be considered, at least in Europe, I'm considered a very difficult fNIRS subject. Thomas will talk a little bit later about how important it is to have an all-inclusive system that works on all participant populations. But I will go ahead and put the cap on my head, just spread the hair a bit. In terms of the cap setup, what we are looking to do is to get really good optode skin contact. So sources and detectors are commonly also called as optodes. And our goal here is to get through the hair and make nice contact with the skin. That's all we actually care for. So right now I don't have anyone to assist me. So I'll do a little trick and get the optodes through my hair. Now, I do not expect perfect signal quality in all the channels, just because, you know, I don't have anyone to assist me, but let's take a look together how it looks. Right. So in terms of setup, that's all you have to do. Most of the times you will prepare the cap in advance before your participants come to the lab. Once you have the cap ready, you make them sit. It's not EEG, you don't need gel, you don't need anything. Just put the cap on and you're actually good to go. I will now share my screen to show you the software part. Here's my screen. My screen is visible now to everyone. Right? Okay.
Yeah.
So I'll just go ahead and basically record some data. The cap I have right now is on the motor region. So the one thing about fNIRS is you can record from any part of the brain. Also depends a little bit on the system, but most equipment gives you the flexibility to arrange optodes over your brain region of interest. So could do prefrontal, and then later in the day you could measure from the motor area, and tomorrow you can do an occipital study. Right now I have optodes on both my right and left motor hemispheres. You see there's nothing in the middle, just left and right. The reason for motor is I will be able to show you some sort of activation. If I do this, then hopefully we'll see something happening. Right. I'll go ahead and record some data. See how it looks.
And Mahipal, I just wanted to mention also that we do have whole head systems as well. So you can cover the entire head, even with very high resolution coverage.
Absolutely. And this is to give you a very brief, rough idea. What you see on the screen is in color red is oxyhemoglobin. So how much hemoglobin has oxygen. That is an indication of brain activation, actually. In the blue, you see deoxyhemoglobin, how much oxygen, how much hemoglobin is lacking in oxygen. And right now I'm talking in this nice sinusoids you see, that's my heart rate. And that's an indication of how good the contact is, how good the sources and detectors are in contact with the skin. So it was a few minutes. During an experiment, I will spend few more extra minutes just to make sure that all the optodes are rightly set up, but it doesn't take too long. Just to give you a brief idea of how an activation will look like if I sit silently and then press my hands together. And then I let go. And press my hands again. see, there's a nice real-time correspondence to what I'm doing right now, to what we can already see. And this is some single subject, single trial. You would want to do more subjects, you would want to do more trials. But Thomas will talk a little bit more about how the hemodynamic response develops, how it looks like. From my end, I will, just to summarize things, a cap looks something like this, consists of sources and detectors. They are mostly arranged in a matrix. Sources send light into the brain, detectors detect light back. And they can be arranged on any part of the brain, any region of interest that you want to study. You can place sources and detectors. Since you don't need EEG, you don't need EEG gel, the setup is within a few minutes, as I showed you just now. For me, from my side, that's all.
Mentioned before. Yeah, just to emphasize a couple things. If you had more questions about what can be done during a remote demo, we're happy to go in much more detail and schedule something with you. So please do get in touch on that if you'd like to see more of the technology. We're really happy to do that. Now, basics of neuroimaging with fNIRS. What is fNIRS? We kind of jumped into it, like I said, because we wanted to make it interesting for you all right away and be mindful of your time. But let's get a little bit more detailed now. fNIRS does stand for functional near-infrared spectroscopy. That's already been mentioned a bit. It is a form of functional optical imaging used to measure superficial blood oxygen levels from the cortex. You can see a side angle here of the brain, you've got the scalp and the sources and detectors there with their connections shown. Data are generated through lightweight optical probes, light sources and light detectors that send light into the brain and read back what has been reflected. So we see the top left image there. We also see an example of a high resolution tomographic fNIRS example, again, overlaid onto a structural image, MRI there. Here we see a more typical 3 centimeter spacing between the probes, still quite good resolution though. And it can be used on all kinds of children. Bold fMRI, by contrast, is blood oxygen level dependent fMRI, functional magnetic resonance imaging. It is considered the gold standard form of all functional neuroimaging methods. Electromagnetic imaging used to measure whole brain blood oxygen levels and anatomy. We like to contrast that with fNIRS, as I mentioned, which is just functional. But it is much less expensive than bold fMRI and has been validated against fMRI in EEG studies as well. We see EEG fNIRS studies together for cross-validation. Now, I wanted to talk a little bit about just the advantages, summarize those versus fMRI. It is more flexible for its environment and stimuli, does measure more components of the hemodynamic response, that's already been mentioned. It is more robust to motion artifact. You saw Mahipal able to talk and move around a bit. Of course, with fMRI, that's not a possibility, and we can even move much more than that and still maintain good signal. We can image a greater range of subject populations. Infants, neonates in particular, very difficult to image in fMRI, but there are also other sensitive subjects that may be challenging due to prosthetics or other reasons that are very much easier to image with fNIRS. It's better comfort, better sampling resolution, and it's a different cost, certainly. It does vary by region. So hemoglobin protein is what we're measuring, specifically looking at whether it has oxygen or not, and it is the oxygen transporter throughout the body. Continuous wave fNIRS systems, it's a type of fNIRS, does measure the relative changes of hemoglobin in the blood. fMRI also measures relative changes in deoxyhemoglobin. Oftentimes people ask for absolute measurements. That is possible with certain types of fNIRS systems. Specifically, you can achieve that with a time domain, frequency domain, that's possible as well. But these are less common methods. One of the main reasons is especially the expense of the hardware and susceptibility to motion artifact. You have to have everything incredibly well positioned and stabilized. So the movements that we saw with Mahipal and the naturalistic capabilities end up being very, very limited with a time domain and frequency domain system, in addition to that much greater expense. So All but one major commercial manufacturer do offer continuous wave fNIRS systems. That's the bulk of fNIRS studies as well as a result. Now, why use near-infrared light? Here we see this window of fNIRS frequencies. That's around 690 to 850 nanometers specifically. That's a window that can pass through tissue. Near-infrared light is more absorbed by the deoxyhemoglobin, that's at HB, or oxyhemoglobin, O2-HB, oftentimes called HBr or just HB and HBO, versus other tissues. Now, all fNIRS systems use at least 2 wavelengths in this range to differentiate oxy and deoxyhemoglobin. You essentially need 1 wavelength per variable that you're trying to identify. So there are oftentimes more than 2 wavelengths, and NIRx does offer up to 8 wavelengths for systems as well, though most people are just opting for 2. Now, a little bit about the hemodynamic response. With neural activation, we are measuring just the oxy and deoxyhemoglobin, as I already mentioned, and we infer that neural activation based off of these changes. So here we see an example of the increase in oxyhemoglobin and decrease in deoxyhemoglobin that we would see after a stimulus. So you have 0 to 4 seconds, and for you EEG researchers out there, you might be saying, wow, how could you possibly ever get anything done with such a long waiting period? And it really has to do with the study design. We are very, very good at localizing different brain regions with fNIRS, but of course, because we're measuring blood flow, you just have to wait for that blood to pump to different parts of the brain. You can't get those millisecond and hundreds of milliseconds types of responses in fNIRS like you can in EEG. But we see a lot of mixed design types of multimodal integration where you can do some fast change types of events in addition to these slower changes or these blocks to look at the fNIRS types of impact. Now, let's look at how light travels between the source and detector. Light leaves the source and travels in all directions. Photons are scattered and absorbed. The average path of photons that reaches the detector is called the photon banana. We already saw that earlier. Here's the example again. Spacing the probes further apart yields greater depths measured, but also reduces signal to noise ratio. So the further we get deeper into the brain, but less signal. And there is a limit to that. Now, the photon banana is traveling through scalp tissue as well as brain tissue, both of which contain hemoglobin, of course. So we need to be able to identify that. If we're trying to just focus on the brain activation, we need to know what's going on in the scalp as well. And there are a lot of ways to do that. One of the best ways is a short channel detector. Essentially, you have the spacing you want to get into the brain, and then you have a really short spacing between some sources and detectors to just measure the scalp blood flow. I did want to talk about tomography, which is an example of what I just mentioned, so multi-distance measurements. A standard measurement is 2.5 to 3 centimeters that Mahipal mentioned earlier, using a fixed distance grid. That's what actually he had on his head, was a 3 centimeter fixed distance grid. You also can vary the distances for higher resolution imaging, up to 3 centimeters or so. You can go a little bit more than that, and we'll get into that later on, under what conditions. And we see examples of a higher resolution tomographic result there. They have been as good as 7.5 millimeters. I referenced the Habermel et al. Paper from which I draw that. So that is incredibly good discrimination of the right thumb and pinky in somatosensory activation. We do want to, of course, talk about challenges that you should consider, because if you don't understand the challenges, you might end up really having issues with fNIRS and thinking that it's not as good as it really can and should be for your studies. Now, light penetration does depend greatly on the thickness of the scalp, skull, and cerebrospinal fluid. You may not be surprised by that. Here we have from the Brigadoy et al. How short is too short paper, examples of adults and infant heads with scalp, skull, cerebrospinal fluid thickness modeled. You have a slightly different scale here, 0 to 25, 0 to 15 millimeters. And you can see that there actually is a pretty big variance between, for example, the forehead and the crown of the head in an adult, being roughly 11 millimeters or so, up to even 22 millimeters. That's a greater distance for that light to travel through, greater thickness of, in particular, the skull for which is also absorbing light. So we need to be mindful of that, because that greatly will impact your signal quality. And that is why you see most fNIRS systems, or a lot of fNIRS systems, I should say, that are forehead-only systems. It's very, very thin in the forehead and easy to measure forehead, but that's not the only reason. Of course, there's no hair on the forehead. So that's the other reason why we see a lot of forehead-only systems. You don't need very sophisticated hardware by comparison. Once we start wanting to measure the hairy parts of the head on an adult, especially near like the somatosensory cortex, parietal areas, you do need to have some pretty sophisticated and high-end hardware to achieve good signal. Darker and thicker hair is more difficult. It's absorbing more light. The roots of the hair can be just as much of a problem, so it's not just longer hair is harder. Even very short hair can be, actually that can be even more difficult if it's causing the cap to lift off the head potentially. So you do need to have strong enough sources and detectors, as I've already mentioned a few times here. And that is definitely an area that NIRx has focused heavily on in terms of our development. And I wanted to talk more about source strength and detector sensitivity here as well. Now, when you have better strength of your sources and sensitivity in your detectors, this does lead to better signal quality and possibility for slightly greater spacing between your optodes and measurement depths. The max spacing that we have seen is around 8 to 9 centimeters over the prefrontal cortex. This was with the NIRScout system. This is actually a much larger system that we have that plugs into the wall with avalanche photodiode detectors, and would be about 4 centimeters beyond the surface of the head. fNIRS has been used to measure, for example, the orbital frontal cortex, which is somewhat deeper than a lot of these more superficial areas that are typically measured. While we know that we can measure deeper structures, it's not just getting that data. We also need to actually, of course, piece out all those layers between that depth up to the surface, the deepest point up to the surface, and validate that against other techniques as well. And that's being done all the time. Cable length is a factor, especially if you're going to be doing concurrent MRI and MEG studies. That would be just fiber optic cables, not lightweight probes like Mahipal was wearing. But still important to recognize when you're using fully fiber optic glass probes, those do reduce signal. We typically see around a 5% signal degradation per 1 meter. Once you get 7 to 10 meters going in both directions, so from the amplifier through the waveguide to the participant that's lying in the MRI and then back, so going through their head and then back, you have light going that whole direction. You get a lot of signal loss just from that fiber. So again, a reason to have good sources and detectors. Other headgear challenges. Environmental light can be a major factor. Of course, we're measuring light. That ends up being actually a source of noise. So infrared trackers, such as motion trackers, TMS trackers, eye trackers, sunlight, and even room light can be a problem. We do use overcaps to block this light. So you see an example here, and that helps tremendously and can be incredibly effective. Furthermore, we use software recording solutions to isolate environmental noise from fNIRS signal. We're able to tell right when we're setting up the system, how much environmental noise is there right now? Is it actually a problem? Is there anything that we can do about it? Which is really critical. Cap fit and size is also important, of course. I don't want to spend too much time on that, but it's somewhat obvious if you've ever used any sort of cap-based solution, EEG, TDCS, and so on. Of course, if you have poor fitting headgear, this can cause probes to wiggle, being out of place. This, in our case, changes the photon banana path and really greatly affects the signal. Of course, you need all the right sizes and have it fit comfortably. Now, probe challenges are also important to consider. They need to easily penetrate through the hair in order to make contact quickly. So we offer multi-tipped probes as one example. We also do single-tip probes, but these can quickly and comfortably get through the hair. And we also offer blunt tip probes for example, bald subjects or more sensitive people that really don't want to have any sort of sensation of a pokey thing on their head. And finally, you do need enough probes to cover your entire regions of interest. This is a 64 probe setup to cover the entire adult head using that 3 centimeter spacing. We actually can go all the way to 160 probes total, so 80 sources and 80 detectors with that system that Mahipal was showing. Now that wouldn't be just that one amplifier, you would string together actually 5 of those amplifiers in that case, but you certainly can get a very high resolution image in that case. Movement related noise, of course, unsurprisingly, can be an issue in fNIRS, just like any imaging technique. So as already mentioned, you need to have the probes remaining orthogonal to the surface of the head. Otherwise, the photon banana path does change, causing noise in the data. You see the little wiggle there. And these spikes are examples of motion artifacts that we created just to show an example where a participant shook their head at these different time points. So it's not a saturation effect that we see, but it is still noise that needs to be dealt with ideally just by avoiding the noise altogether by having a good cap setup. But of course, it's not always possible to prevent all motion artifact. So there have been a number of ways that we can deal with that as well. It is possible to have good signal, but it's not that simple to stabilize the probe. So you want to be careful to ensure that you select a system that has good stabilization techniques. There are systems out there that can do that. I did want to talk about industry-wide strengths of fNIRS. We've touched on some of them, but it's good to just cover those again in case any of them were missed and summarize them again. It is safe and non-invasive. There's no scalp abrasion, although sometimes you can not abrade the scalp, actually part the hair. So you can take a probe out and go in and part the hair in case you're really not getting good scalp contact with the probe. You saw that was not necessary with Mahipal in that measurement, but it's something to be mindful of. We used to have to do that with our systems all the time 5-6 years ago. There is no gooey gel. It is lower cost than fMRI for hemoglobin data. It doesn't require specialized techniques to operate. And fNIRS technical support does vary quite a lot, substantially by manufacturer. So some groups, a lot of companies will provide some technical support. Some don't provide hardly any. NIRx does pride itself on providing very intensive technical support to help groups get up and running, even if they have no neuroimaging experience whatsoever. And another strength for the industry is that there's a very rapid growth in grants and publications that we've seen by percentage relative to other techniques. So it's really a very fast growing, and as we've seen, the fastest growing major neuroimaging technique. Now, system dependent qualities is also an important thing to talk about when we talk about strengths of fNIRS. You can use it in many different applications. Again, this depends on your system, but we've seen, of course, neurorehabilitation, neuroengineering, BCI neurofeedback, and on. So very, very similar to what has been done in, for example, EEG. There's a lot of overlap for sure. There's some nuances in the technologies, but yeah, it's a very good comparison there. For multimodal compatibility, we see fNIRS being combined with EEG, fMRI, pretty much you name it in terms of imaging, it has been combined. Virtual reality, augmented reality as well could be added to those, to this list. The scalability is another system-dependent feature that can be really nice for labs. So you can start with a very simple, low-density configuration and scale all the way up to something that's very high density, even measuring multiple subjects simultaneously. Start out without fMRI compatibility and add that in. That makes it very nice for researchers that maybe just get a small grant initially. They want to start using it to incorporate it with, let's say, an existing EEG headset or TDCS headset, and then invest in more to go higher resolution or cover more regions of interest. I talked a little bit about data quality, or a lot maybe already, but that does vary a lot between systems. Resolution also can vary quite a lot between systems. That's just a couple points to be mindful of always. There is lower susceptibility to motion artifact than fMRI or EEG. I put this under system-dependent strength because it just varies. You really should check out the system specifically, at least see some sort of remote demonstration at a minimum if there's a video that can be shown, because it really does vary. This is something that we've seen big differences between systems. It does have a faster setup time than many other neuroimaging techniques, and it can be very, very comfortable. So yeah, that's a good one when you get a chance to try it out. I definitely recommend trying out a good system and seeing how that feels for you. It can allow for real-world naturalistic environments and tasks. We see a couple examples there. We already saw some examples of those naturalistic tasks earlier with the case studies. Social interaction studies and the ability to bring systems to participants is actually a really, really big area of growth that we've seen with COVID-19 restrictions, that many of our end users have asked about bringing systems to participants to different nursing homes or schools or wherever. And this has really been, I think, a big area of growth this year for fNIRS, given its portability, given again that fMRI is not a portable solution. Now, getting into some additional case studies. Just want to double check my time here, doing pretty well. This is a robotic exoskeleton evaluation looking at cortical activation. They did see an increase in oxyhemoglobin in the right frontal cortex in the passive compared to the active conditions for deoxy. They saw some differences as well. I don't want to go through all of it, as you'll have this information and the video, and you see this was Peters et al. This is a sensory motor evaluation post-stroke. They did see an increase in sensory motor activation with decreased motor performance during functional upper extremity tasks. This is one where the title really nicely describes the results. And we've got a robot assisted walking and gait analysis using fNIRS. Again, we see the strength of the technology given its susceptibility to motion artifact. To conclude, fNIRS does excel with movement. It's a very fast setup. The localization is as good as 7.5 millimeters with specialized probes in that case, but we still can get very good resolution. Naturalistic ergonomics and studies, combining with other modalities like motion, EEG, EMG, real-time imaging, such as BCI and neurofeedback. You can measure a variety of different subjects and different experimental conditions. So with that, I'd like to thank you all.
It was a very beautiful, very nice, very interesting presentation.
That's very kind of you. Thank you.
Very nice presentation, and Dr. Chaudhary showed it. It was awesome, mind-blowing. Just I was glued to the machine, seeing the changes in the hotspot diagram. It was wonderful. Thank you. And I'm already asking you so many questions, and you have been, both of you have been patiently answering, because it's a very interesting topic today. And Dr. Datta connected you with us, and so nice of Dr. Datta to bring you on board here. And we'll be in touch. I am planning to go ahead in this, and we'll be in touch shortly. But thank you for your time today.
It was fun.
Yes.
Thank you very much.
Bye. Bye.
Yep. Bye-bye.
Thank you. Bye-bye.